it actually recording?
No, please press the record button.
Okay.
Thank you, Ben. Thank you very much for coming by and spending an afternoon listening to my thesis topic. It is on heat transfer in a beryllium core. My name is Isidore Silver, but I go by Izzy. I'm a master's candidate in nuclear engineering here at Idaho State University. And without further ado, I'll go ahead and proceed. So what I'm going to go through now is a simple outline of what this thesis is going to entail. I will go through a quick introduction where I'll talk about the problem statement, the initial condition of why there was a point to even doing this heat transfer analysis for beryllium core in a Mars Hopper rocket. Then I'll talk about the theory that was used to construct a model that was used in the spreadsheet to do calculations on temperature changes, heat transfer, thrusts, and other items of interest. I'll go through a short procedure of the calculation, essentially how the spreadsheet calculated the results. Then we'll look at the results of each calculation. Then what I got in my spreadsheet, I'll show the comparison with RELAP 5 3D, and we'll compare those two outputs and see how similar they came to each other. I'll finish up with some concluding remarks, talk about conclusions that can be drawn from the study, where I believe that research should go next to build on or even further investigate, and then I'll open it up to questions. So, the problem statement is that Mars rovers, Spirit and Opportunity, they've been on Mars for about 5 years, and they've traveled about 5 and 10 miles respectively. Now, Mars is much bigger than that, so the question comes up, what's a more easier way or even a better, faster way to explore Mars, gather scientific data on atmosphere, soil composition, even look for water and polar ice caps? So the idea that was brought up was to have a small hopper rocket that would use compressed CO2. It would fire down through a heated beryllium core, and it would make a transit of 6 miles. Then the core is loaded with a radioisotope. The decay heat heats it up, and 3 days later, it can blast off again, after which sucks more carbon dioxide from the Mars atmosphere into its tanks, blast off, transit another 6 miles, take whatever samples, measurements that can be obtained, or that is your objective. So the point design of the project that was given was that we have one tank of compressed CO2 compressed to 20 times atmospheric pressure, contains 22 kilograms of carbon dioxide. We were told that there needs to be a burn time of about 22 seconds, and that there needs to be enough thrust to essentially lift the hopper up. Now that's achieved by increasing the outlet temperature of the CO2 as it blasts down through the core. There was no initial design on, does it just flow around a big chunk of beryllium? Do you drill holes through the beryllium? Do you make corkscrew holes through the beryllium? Do you need to add fins to it? So essentially, here's a scale model of the beryllium core. This is Susan. She's the average height of a person, and the beryllium core here is about 15 centimeters high. So it's very small, but it contains about 6 megajoules of heat, heated to 1200 Kelvin or about 1700 degrees Fahrenheit. So what I came up with was just a very simple case for an analysis, and you have a beryllium core, not a critical core, just powered by decay heat from radioisotopes, and you have 105 holes going straight down through it, no fins added, just to see would it be able to take all the heat out of the core necessary. And if there were problems that arose from that, like couldn't get enough heat out, then to modify the design afterwards. And that became my analysis was to essentially look at each flow channel, say, okay, what's happening, and then use the information from that flow channel and then model what was happening into all the other flow channels of the core. So the theoretical analysis that was used to construct the spreadsheet consists of two sets of engineering equations. One set was compressible flow equations, and that I'll go through that, starting with the control volume that you look at for general fluid mechanics. Then I'll discuss how that we can use that to then get relations for ideal gases. Then I'll talk about two specific cases, one called phantom flow, which is if you just have a compressed gas flowing down a tube where no heat is being transferred and the only changes in energy come from friction of the tube. And then in the second case, which is called Rayleigh flow, is heat entering the tube. And there's so much heat entering the tube that you can essentially assume that it's a frictionless pipe. The other set of equations that I use to create my spreadsheet of heat transfer relations were using convective heat transfer, using a heat transfer coefficient, which had to be determined, and taking that and equating it to an energy balance, which could then be used, so with these two relations, then to look at the change of energy to predict what was happening to the gas as it flows down the pipe in case 2 of Rayleigh flow. So with the compressible flow relations, if we look at a control volume, this is a fluid flowing down a pipe, and we want to examine what's happening in it. What we can do is look at just a small control volume and look at the equations that govern that. So we have conservation of mass with a mass flow. The mass entering the volume is equal to the mass exiting the volume. We're not adding any mass to the control volume. The second is conservation of energy with enthalpy, kinetic energy, gravitational potential energy, heat, and essentially the same on the other side for a different point, and shaft work. There's no work in any of these tubes, therefore we can neglect that term, which I'll talk about later. Now for entropy, Billars and Zucker, for their theory, they break entropy into two categories. Entropy due to irreversibilities such as friction, and entropy due to changes in heat, which can then be equated as heat, the traditional form of entropy, plus irreversible entropies due to irreversibilities. This is a pressure stagnation pressure energy equation, which I'll talk a little bit more, but that's used to create the further theory of phantom flow and Rayleigh flow. It's not easily recognizable in those two theories, but it's used to go and build that theory. Then we have stagnation enthalpy, which I'll talk about what a stagnation property is in a second, which is equal to all the energy that a fluid has as it moves down a pipe. And then here we have basically, once again, a conservation of energy using stagnation properties. So what is the stagnation state? Well, let's say we have a sphere and we have flow moving all around the sphere, and there is one point on the sphere at the very front where the flow will hit it and it will take all that energy and stop. So if we have these properties, enthalpy, temperature, pressure, if you could take all that energy and essentially stop it at one instance, and then look at the enthalpy, temperature, and pressure, that is what's called the stagnation points. Now, the stagnation point is important because you can then reference your static properties further back into the system if you know the total energy that a system had itself at a point, which is called a stagnation point. So, going from a control volume, now if we look at the relations for an ideal gas, we want to define what's called a sonic velocity here. which is a function of the ratio of specific heats times a factor called GC. You really use that if you're using English units to deal with that 32. Then we have the universal gas constant for whatever gas. It will change if you're using CO2, hydrogen, whatever specific gas you're using, but these are all generally constants. And so the sonic velocity is generally a function of temperature. Now, if you take the square root of the sonic velocity, you end up with the Mach number, which is also equal to the velocity, which you can then put in a ratio of the actual velocity of the gas over the sonic velocity, and therefore you arrive with fractional Mach numbers such as Mach 0.45, Mach 0.7, Mach 1, Mach 1.25. Then we have our other properties, the stagnation enthalpy, the stagnation temperature, stagnation pressure. Here's a modified form of the stagnation pressure energy equation from the control volume. Now we're looking at it for an ideal gas. And this last property, which relates to pressure stagnation states of a fluid, to the change in entropy divided by the universal gas constant, all to the power of an exponential. So if you tabulate these values, you end up with this chart. So for instance, if your fluid has a speed of Mach 0.1, if you look at what the ratio of the pressure is at where it is in its static state versus its stagnation state, which is a reference point, we see that it's 0.9994, which that's fine, that's just a tabulated value. So you can say, okay, here's what your static pressure is, because we know either A, the stagnation pressure, the static pressure, and we know this ratio. So if we move on to the case of Fano flow, here's a short graphic to describe essentially what's happening. This is a TS diagram, and there's two legs of this curve, which get broken into subsonic flows on this top and supersonic flows on this bottom. Now, what's done is we define a reference state, but instead of using the stagnation properties, we use a state called star, which is if the fluid is at Mach 1. Now, this is done with a regular duct. So if we have fluid flowing down a duct of any given length, can be anything. To create this reference state, what we do is how much more length of pipe would be required to get it to this state of Mach equal to 1. And that's how these curves are constructed, and that's how the theory is constructed. So we can look at the relations for them. So once again, here's our reference state, and this is our reference state ratio of T star, which is the static temperature of Mach 1 compared to what the static temperature of the fluid is, further up the pipe. And we can do the same for pressure, density, stagnation pressure, and this property right here, which is the FL max over the diameter, that actually relates, since we're talking about frictional pipe flow, this relates to the friction factor, the diameter, and the length of the pipe. Now this FL max over D, for my specific case, was at a value of 0, and that happens because in my model, the change in pressure was so great that there was a choked flow condition at the end of each tube. Therefore, I could then back out, okay, if I just have frictional pipe flow, what speed was it at the very beginning entrance, and then I could look at all the properties as it moves down the pipe. So if we tabulate these values, you can see that at very low Mach numbers, the FL max over D gets very large. And here's some values of static properties. And then the FL max over the diameter gets much lower as you approach Mach 1. So if we look at the second case of Rayleigh flow, what you have now is that you have energy being added to the system. And that energy is from heat. So this actually changes this is the stagnation curve for subsonic and supersonic flows. Your stagnation properties will actually increase because you're adding energy to the system. And if we look at the energy of the system at one point compared to another point, if you add heat to it, we're assuming the energy is conserved, so we have to take that into account. Now, this does have some interesting influence on the static properties, because the temperature of the fluid will increase up to a certain point. At that point, any additional heat added to the fluid will not increase the temperature, it'll decrease the temperature slightly and just add to the overall energy of the fluid itself. So all that heat energy essentially gets converted into velocity that accelerates it to Mach 1. So here are the relations used for Rayleigh flow. Once again, pressure, temperature, density, stagnation temperatures, and stagnation pressures. And the table of values can be seen here. So for a given ratio of static temperatures, stagnation temperatures, densities, stagnation pressures, you can say, okay, if my inlet pressure is this, or a pressure at 0.1 versus the pressure at 0.2 is this ratio, I have a fluid moving at this Mach number, or this velocity. And so, let's move into the other set of equations, the heat transfer relations, that will then be able to tell us exactly how the Rayleigh flow develops in these tubes. So starting with Newton's law of cooling, which is essentially the heat is equal to a heat transfer coefficient times the surface area of the pipe times the difference in temperature between the 2 points, gives us the amount of heat transferred. The heat transfer coefficient is related using basic convection heat transfer relations with using the thermal conductivity, the Nusselt number, and the diameter of the pipe. And the Nusselt number is broken once again into a Rayleigh number and a Prandtl number. The Rayleigh number and Prandtl numbers are used to describe the flow as it moves down the pipe. And this factor right here is due to the fact that it's a gas, not a liquid, so it's times 0.021, gives us our Nusselt number. Once we know our Nusselt number, we can find our heat transfer coefficient. And so, using conservation of energy to look at the heat transfer, we see this is the basic equation. Heat is equal to the mass flow times the specific heat times the inlet and outlet temperatures of the given length of pipe that you're looking at. And there's two modes. There's if the surface heat flux is constant, and there's if the surface temperature is constant. I wasn't given any heat fluxes. I didn't know any heat fluxes of the heat going into the pipe to then heat the fluid. So I assumed that over the length of a certain segment that the surface temperature was constant, and thus used this relation of heat is equal to the heat transfer coefficient surface area times the average temperature or difference, where that is the surface temperature of the pipe minus the bulk temperature of the fluid, which is essentially an average temperature of the fluid. And so how does this all relate back to Rayleigh flow heat transfer? Well, if we take our large Q and divide it by a surface area, we get what's called small q here. Now, the heat transfer in Rayleigh flow, this is the theory behind it, that the stagnation enthalpy at one point plus an input of heat gives you the stagnation enthalpy at the second point. Stagnation enthalpy is equal to stagnation temperature with this relation. So we can say that a given transfer of heat causes a change in the stagnation temperatures. That is important because it is not equal to a change in the static temperatures. So the static temperatures I could pull out using those relations, but for the transfer of energy, the transfer of heat going into the CO2, I had to look at the stagnation temperatures exclusively for each section. So for the spreadsheet model, this was the basic geometry. You have a 15 centimeter tall block of beryllium shaped into a cylinder. Its diameter is 12 centimeters, and each of these holes are 2 millimeters in diameter. Now, some inlet boundary conditions for each hole. I assumed that the temperature of the tank was constant. This created what's called an isothermal blowdown scenario, and that any pressure changes in the tank of compressed CO2 took place. The change in pressure, I used the ideal gas law to calculate the new pressure per mass of CO2 had left through the core. So the segment calculations, what I did was I broke each tube into 30 segments, half a centimeter in length. I made the assumption that the surface temperature was constant over that length, and essentially created a mesh that I could use to calculate all this energy transfer going around this beryllium core into the CO2. Now, the exit conditions for one section became the inlet conditions for the next section, which I hope this graph will illustrate that further. So, if we have cold CO2 coming into the first section, a certain amount of heat is transferred. We have a static temperature, Mach number, pressure, static temperature, so on. And so heat gets added to it. Our new properties are a new temperature, Mach number, pressure, so on. And as it leaves this section, it becomes the inlet inputs to this section, which then leaves this section, becomes the inputs to the next section all the way down till we get to the end of the pipe, where because of the pressure difference between what's in the tank and Mars atmospheric pressure, it's a choked flow condition, so it is Mach 1 at the exit. Now, all the equations and relations that I talked about before assumed a definite time interval so that there's no change in the property over, it's not a direct d whatever property dt. So the way I constructed a transient calculation of what happens over this 22 seconds was that I created essentially a quasi-steady state model, which is that for a given time interval, I assumed it was steady state, went through the calculations, looked at all the changes in energy of the core, what the change in the mass of carbon dioxide in the tank was, and then use that as the inputs for the next times interval calculation. So for second one, I went through, got data out, used that data to say, okay, for second number 2, and walked it through the same process, and for second number 3, walked it through the same process. The last heat transfer calculation I did was I took away a instantaneous heat transfer through the core so that thermal conductivity was not essentially infinite, and tried to model what would happen in closer to an actual scenario where the top cools off faster than the bottom, and I'll discuss more about that in the slides that follow. So here is the temperature of the beryllium for an isothermal blowdown scenario. At time t equals 0, it's at 1200 Kelvin. What it should be, that was what was given. And then as we step down, it makes a nice gentle curve, which is expected for an isothermal blowdown. And by about 13 seconds, we're starting to lose a lot of heat transfer, as a lot of the heat has been already transferred out of the core. The temperature of the beryllium is around 300 degrees Kelvin, and by 17 seconds, it is essentially a cold gas jet. This is the outlet temperature of the carbon dioxide. This was important to graph because the rocket equation for rocket thrust tells us that the velocity of the gas leaving a rocket engine is proportional to its temperature. The higher the exit velocity, the more thrust you have, therefore the higher the temperature, the higher the velocity, the higher the thrust. Now, you do get pretty high CO2 outlet temperatures at first. That's about 1063 Kelvin. And then once again, as I showed in the beryllium graph as well, that the heat tapers off very quickly. And so about 16, 17 seconds, you're at a cold gas jet. These are some thrust curves. So once again, looking back at the total amount of thrust that you can get out of this, this is for a blow straight through, no nozzle attached to the beryllium core, and you get a top thrust of about 500 newtons. Whereas if you could modify the core so that it flows nicely into a nozzle and accelerate to about Mach 2, you can get about 1500 newtons, which translates to about 142 seconds of specific impulse. The only reason why that number is important is because that was the goal of what they wanted to accomplish using the heating the CO2 and then blasting off. Here is the axial conduction curves, which is the last calculation I did to try and model conductive heat transfer through the beryllium core. If we look at the first section, it cools off very rapidly as would expected, and the other sections cool off slower than the first section, but by 7 seconds they're all pretty much cold. This is a graph of the CO2 outlet temperature assuming axial conduction versus infinite conduction through the beryllium. As you can see, we have our nice gentle curve for assuming infinite conduction through the core, and at 7 seconds we have a very drastic change in the outlet temperature of the CO2 as expected, since in the axial conduction the top cools off fastest, so that the CO2 is taking all the energy out of the lower sections of the core. This is the exit thrust for the beryllium disk, assuming conduction effects. Now these curves, as you can see, are not gentle curves that essentially trail off. They do have humps in them, and as I graph that in comparison with beryllium, where the thermal conductivity is infinite, you still see those. These are artifacts of the theory that I used. I don't think that the theory that I used to model the axial conduction is as accurate as it could be. I'm not sure if that's due to the fact that I only divided into 5 sections instead of 10, 100, approaching essentially and looking at it from a continuous section. So dividing into sections, but looking at it as a continuous disk. But those are artifacts, and therefore those are errors in the theory assuming axial conduction. Now this is a thrust curve to say how close can you want to get to a cold gas thruster? Can you just approximate it as a pressure tank that just opens to Mars atmospheric pressure? This was using 2 different Mach numbers for the Fano flow, and the red line is if you just approximate just a nozzle of a single area, and if you notice, they begin to converge. So I believe at a point it is safe to approximate the cold gas jet as if it just exited through a nozzle of no length. So the comparison of my spreadsheet with the RELAP 5 model, Dr. Richard Schultz of the INL was kind enough to model these tubes in RELAP 5 3D. And he used the same inputs that I did, and he divided his model into 20 sections and got all the information, the heat, the change in temperature of the beryllium, which I will go ahead and show right now. So for the beginning, middle, and end sections of Dr. Schultz's analysis, we see that they are once again just nice curves that gradually trail off. Now, there was some error at around 11 seconds, and that was because my assumption that I was given was that assuming that is a gas the entire time that the blowdown occurs, what RELAP 5 was telling was that at that point you're starting to get to the triple point of CO2, so you were getting multi-phase flow, and thus it errored out. But in comparison to the data that I came up with my spreadsheet, once again, here are the beginning, middle, and end sections of beryllium, and my curve is this orange curve, and it lies right in between the beginning and middle sections in regards to beryllium temperature, and thus those curves are very similar and give some confidence to my calculation. So I'll just go ahead and finish up and say that the theory that was used to model the spreadsheet was steady state one-dimensional theory that I modified into a quasi-steady state one-dimensional theory. After looking at the results for the beryllium temperature, I don't assume there's that many changes if you go to multiple dimensions, essentially taking 2 and 3 dimensional compressible flows into account. There may be some changes, but overall the curves look very similar for 1D compared to RELAP 5 3D. Also, my analysis didn't take into account thermal expansion shocks that you get when you heat up a gas really rapidly, and therefore those need to be looked at and possibly accounted for. With a straight blowdown straight through a beryllium core using the design I made, that it is not enough to lift the rocket to the necessary trajectory of 6 miles that they were looking at, and therefore they would need to either have a nozzle designed such that as the flow leaves the beryllium core, it is able to be accelerated to a higher velocity using rocket nozzles, or perhaps a redesign of the core such that you have so many larger holes, like instead of 105 small holes, you have maybe 5 larger holes, and attach nozzles to each of those holes as well. And with that, I'll go ahead and open up the floor to questions.
Anybody can ask any questions.
Okay, go ahead, Ben.
So, I know your analysis was for all the heat transfer and flow, but for the core, you said it's made out of radioactive isotopes. Do you know which types they were shooting for?
The initial problem statement and point design, they were looking at plutonium-238, strontium-90, curium-244, and
Mixture or individuals?
The strontium was a strontium titanium titanate, so SRTiO3, I believe, and then the regular, I believe, plutonium oxide for the plutonium-238 pellets, and I'm not sure what forms they were looking at for the curium, and there was one more isotope, but I think it's americium. Americium.
And then, what's the point of the beryllium?
The beryllium essentially acts as a giant thermal capacitor. So you charge up this beryllium over time, and then you blast it all off using it just like a capacitor in like a circuit to charge up a circuit. And that would just give you enough to transit, and then you recharge once again, blast off, recharge once again.
So does it have a pretty high specific heat then?
Yes, it does have a high specific heat, and the only thing higher than that, metal-wise, would be to go to a different substance like water. And that's one of the main
And it
reasons.
transfers really well.
Right, and it does have good thermal conductivity, close to aluminum, actually.
Is there any kind of controller of the temperature there in the device?
No, essentially it
Because
would
we
be.
told that if the temperature is higher, then the velocity will be higher. So is there any
Right.
controller that
Oh, well, the temperature of 12, like could you go higher than 1200 Kelvin?
yes, yes.
Yes, you could, but the melting point of beryllium is around 1500 Kelvin, I believe. And because of that, just to approximate safety limits of, you don't want the beryllium core to obviously start melting before you can blow the CO2 down through it. So the 1200 Kelvin was just a reference figure, just to say not high, but not high that we're bringing it close to the melting point of the beryllium, essentially.
So it will not exceed the 1200 Kelvin. Never
No.
like that.
And that's due to the fact that as the CO2 moved through, it would pick up that heat, but as I showed in the Raleigh flow chart, at a certain Mach number, you begin to decrease your static temperature as you approach that Mach 1, Now, it doesn't drop off an enormous amount, but it does drop significantly in order to reach that velocity when you're under a choked flow situation.
I have three things, if you could just
Oh, go ahead.
clarify them for the sake of the students. That core is supposed to serve two purposes. It's supposed to run a Stirling engine,
Yes,
right, to compress the CO2
right.
into the tank.
And-
I'm not sure you mentioned, just so they understand.
Yes. So while it's recharging, it's running a heat engine that would thus power any instrumentation that was aboard, any scientific measuring instruments, and to compress the CO2 once again so that it can blast off again.
So what is the heat source of the Stirling engine? I mean, what's the heat temperature? I mean, it's got to be at least 1200 Kelvin because that's what you heat the beryllium to.
I honestly, I don't know if they just pulled a certain amount of energy out of the core at a given time, so it would drop the temperature of the core, but then slowly return. And so basically, that the Stirling engine was using so much energy that it would heat whatever working fluid it's using to a certain temperature, and it would dump that maybe back into the core. I don't know. I really didn't have any.
You weren't given any of those details.
I was just curious.
No, that's fine. That's fine.
Just strange they're using a Stirling engine. I didn't know they had any small developed Stirling engines out there.
Well, I think they were thinking
That's
about it.
That's cool. I mean, that's cool. I've
Yeah.
seen them. I've seen small Stirling systems, but that's.
Well, I heard they were going to try and use a Brayton gas cycle turbine, but that's really only effective when you get to higher power levels. And since this was what's considered a lower power level, they said a Stirling engine would probably be more efficient.
I just usually see them do RTGs. And
Right.
So-
The other thing that might have been of interest, sort of along Ben's question, how much plutonium-238?
That I did.
Where the
There were no like.
I thought they told you in order to get this, you had in some of the original data.
I had a white paper, and in there, in the technical feasibility section, they listed a bunch of isotopes and they listed the power in watts per gram, but they didn't give any. I believe what they wanted was that so within 3 days, using powering a Stirling engine for the electrical components, as well as heating up the core, they wanted to say, okay, how in 3 days we want to reach 6 megajoules of thermal energy. And they, as far as the paper that I was given, they hadn't decided on one, and they looked at, okay, if we use plutonium, we'll probably need to use this much, but they hadn't decided how much power the Stirling system was going to generate and how much energy that would take out of the core at a time so that you could still meet that 3-day recharge mark.
So is the plutonium actually within?
It's embedded inside the beryllium block.
And I'm wondering, so you got a chamber for compressing the CO2, but then you're also running a Stirling engine?
Yes. So the CO2 tank essentially is exclusively for liftoff and for transits, whereas the Stirling engine, obviously you need a way to power the pump to suck the CO2 in, as well as any scientific instrumentation that's aboard.
It has to produce the electricity for that.
Exactly.
using the Stirling engine.
Yes.
And then the last item that might interest the other students, you ought to explain why Dr. Schultz did part of his thesis and you didn't.
Oh. Well, the only reason why originally I had planned to use another computer code because they're still in the process of building a prototype for this, and they've been having a hard time machining the beryllium to basically create a prototype to test out a test rig. So what I was going to do was compare my spreadsheet to a commercial computer code. Well, after talking with some people at the CSNR, which is where I got the heat transfer topic from, the computer code they were using couldn't handle gaseous flows that were faster than Mach 0.3. So you were getting to that barrier of, well, we can't really approximate it as an incompressible fluid. You're starting to need to, figure out all these relations, and it really affected it. So at that point, I was still trying to, while I did have some confidence in my spreadsheet, I wouldn't just go out and build and say, okay, this will work, send it off to Mars, just on, these calculations. And since there wasn't a rig to test it on, I knew that Dr. Schultz at Relab 5, I did have a course, and it's using it for instructional purposes and loss of coolant accidents where the pressurized heated water essentially vaporizes and you can treat it as a compressible fluid, like in a minor or major loss of cooling accident. So I asked Dr. Schultz can you use it to look at compressed gases. He said that they did have a version of Relap 5 that could do that. Unfortunately, I didn't have a license to work with that. So I asked if he would mind just doing a simple calculation, just so that I have something to compare my results to kind of give some more confidence to what I got as a result versus what another computer code might calculate.
It wasn't a real simple calculation.
Well,
Simple for him.
well, it did take a while because no one had really looked at that type of scenario of having a 2 millimeter diameter hole as a pressurized blowdown for Relap 5. So it took a while to figure out, first of all, how to model that, and then once that was modeled, still trying to make sure that all the inlet conditions were what I had for my inlet conditions, so we could come up with a comparison between the two codes.
Is this work still going on?
Yes, it is. Actually, I talked with Dr. Howe last week. Unfortunately, he wasn't able to make it. He's at a conference today, actually, in Michigan. But they are actually, when I talked to them, they are in the process of trying to build the test rig. And one of the material engineers that they have who's working on his PhD was trying to figure out a way to machine beryllium so that they could come up with a test rig. And they're running into problems with that because beryllium, if you sand it, you have these little beryllium particles that float into the air, and you can get beryliosis. So now they're maybe moving to a different material for a test rig and then machining the beryllium. So they are still doing it, and I talked to Dr. Howe. I told him what my results were, and he was definitely interested in it, and definitely wants documentation on it for their research or what they're doing for the hopper.
They've machined the beryllium at IO.
They're trying to figure out ways of doing that.
And safety people go ballistic for that.
Probably.
Because my experience with machining beryllium is you got to get special shops with special equipment, and
Right.
that's
No,
tough to
they
do.
paid like $100,000 for the ATR core.
Years ago they did it, I know, no questions asked.
But yeah, they also did it at naval shipyards too, and a whole bunch of other places.
Things have changed.
Okay, are there any other
Any other
questions
questions
from
or
Jeremy?
comments or?
Now, on the speeds
Go ahead.
that you're looking at, was that given as to what speed range you needed to be in?
For the
design?
The only thing that I was given in the point design was that you had to have a specific impulse of 142 seconds, and I really didn't go into depth on the rocket equation where that all comes from. But what you can do is using the rocket equation back out what amount of thrust you need, and from the thrust you can back out what speed you need. And now you can get that kind of thrust if you could heat up the CO2 to a high enough temperature, since the sonic velocity of Mach 1 is only based on temperature. The higher the temperature, the higher the exit velocity. Now the limitation of the beryllium is that it does have a melting point, so you can't get past that unless you use a different material, but then you lose specific heat capacity, so your core becomes bigger. So, I guess what I'm trying to say is that yes, you can if you heat up the CO2 hot enough.
Now,
But
you were choked, weren't you?
yes,
Okay, so, I mean, if you had a diverging nozzle, you could,
yeah, accelerate it past Mach 1. Yes.
right, which is what you showed on that one graph.
Exactly.
And I was just wondering if they gave you some design specification, because maybe they just can't go very fast without damaging the structure.
They really didn't give me any design specification, like with the nozzle is what you're asking?
Well, I mean, like if you go too fast, you know.
Right. Well, and you know, that's another thing that I really didn't have a chance to look at because I was concentrating on heat transfer, but
Right.
considering that, you know, obviously you're doing very large temperature differences, I don't know what damage that would do to the really.
Structure.
Exactly. Exactly, and that's something that also needs to be looked at before, or they might be looking at that when they build the test rig and look at, you know, thermal stresses and that.
Well, if there are no other questions, I guess we'd like to excuse the students and everybody but